In this problem, we have a distributed load. The load intensity function, W as a function of X, is given. And we need to use a single force, its resultant force, to replace this distributed load. And we need to specify where it is. So this is the function, Wx function, this right here, this curve. So at any given point, an arbitrary location x with a width of dx, the w value times dx equals to df. And if we integrate it along x, that will be our resultant force F. So in this case, for convenience, I'm going to assume that the force is positive if it's downwards, because we only have downward force. So this force equals to the integration along the entire x from x equals to 0 to x equals to 4 meter. We set w dx, which equals to, integrating from 0 to 4, w is 2.5 x to the third power given by this equation, dx. So this is a simple polynomial. It's not too hard to integrate, so that equals to 2.5 times 1/4 x to the fourth power evaluated from 0 to 4, which simply equals to 2.5 times 1/4 times 4 to the fourth power. So that equals to 160 in the unit of Newton. And then for the moment, we just determined that, we just mentioned this little strip is your df. Therefore, you can calculate the moment caused by this df about point A, and that equals to x times df, because for this small force, the moment arm is x. And then we can integrate it again along x direction, and that'll equal to the total moment about point A. So in this case, we're going to assume that clockwise is positive, because again, the forces are only causing clockwise rotation about point A. So that just makes calculation easier. We don't have to deal with the sign. So clockwise in this case is positive. Just like we said, this equals to the integration of x times df, but df is w dx. Therefore, integrating from 0 to 4, the entire length from at this end, that's x equals to 0, at this end, that's x equals to 4 meter. Okay, so integrating along this entire length, 0 to 4, x times 2.5 x to the third power dx, which equals to the integration from 0 to 4, 2.5 x to the fourth power dx. Again, this is polynomial, not too hard to integrate. So equals to this, evaluated from 0 to 4, simply equals to 2.5 times 1/5 times 4 to the 5th power. And that equals to 512 Newton meter. So we have determined that the resultant force of this distributed load is 160 Newton. And the resultant moment caused by this distributed load about point A is 512 Newton meter. Therefore, we need to place this force at a location that it also creates a 512 Newton meter moment about point A. So if we put it here, this is my 160 Newton force. What is this location x bar, so that this 160 Newton force creates the same 512 Newton meter moment about point A? So because this x bar is the moment arm of this 160 Newton force, so you can tell that it can be determined by taking the resultant moment, 512, divided by the force, and that equals to 3.2 in the unit of meter. So now we have determined the resultant force of the original distributed load. We have placed it at the correct location. So this concentrated force 160 Newton replaces the original distributed load. It is the equivalent system of the original distributed load.